Okay, so we've been dealing with linear functions. And most of what we've had now has all been linear, but we need to know how to identify if something is linear. If it's linear, it has a constant rate of change. Okay, meaning as we go up it is going to have the same change. So let's first review linear function versus nonlinear function. A linear function is one that creates a straight line, plain and simple, and it has a constant rate of change. Something with a constant rate of change, that is called slope. Okay? So pause right now and write that down. A non-linear function does not create a straight line. Often when we graph it, it's a curve. So here's one way we determine linear and nonlinear, and this is pretty straightforward. Does it graph a straight line? The whole graph is straight. So we take a look at number 1, there's a curve in there, so it's nonlinear. If you look at number 2, that is a straight line. It's okay that it's at an angle, it's still a straight line, so it's linear. Number 3 we should look at, it's a U shape. That's actually something called quadratic, which you'll get to next year. But for now, all we need to know, it's nonlinear. Then we hit number 4, and if we look at that curve, that is nonlinear. Okay, so there's another way that we need to determine if functions are linear or not. And if we have an equation, if the equation can be written in slope-intercept form, meaning y equals mx plus b, meaning y must be alone, as long as y is completely by itself, that is slope-intercept form. Both the x and y variables have to have an exponent of 1. So if they don't have an exponent of 1, then it is not linear. So you can look right away and eliminate something. So let's go look at number 5, I'm sorry. So first of all, is y by itself? That answer is yes, okay? And is it in mx plus b form? It is, so this one's linear. Now if I go to number 6, yes, y is by itself, but if I look at x, it has an exponent of 1, meaning, okay, it is nonlinear. That exponent of 2 means it's nonlinear. We'll go look at number 7. Remember it said if you can get it into y equals mx plus b. Right now, y is not by itself. It is in standard form. But if I take my equation and I subtract 2x from both sides, I now have y equals negative 2x minus 5, meaning it's linear. And x and y's exponents are 1. So we got to be careful here, because in number 8, if I got y by itself, I have y equals 10 divided by x. That is not linear. Slope-intercept form is a number times x, not divided by x. That is a different graph. X there does not have an exponent of 1. It's actually a negative 1, and we will get into that later, but you need to write that in. This is nonlinear. Let's go look at number 9. This one's easy because I can add 8 to both sides to get x plus 8 equals y, meaning y is by itself. Both x and y have an exponent of 1, so it is linear. Now, when we come to number 10, take a look at this. X is our actual exponent. That changes things. That's different. So this one is non-linear. I would write in here, x cannot be an exponent. That's a different graph. It's not a linear graph. So let's go look here. Now, I have y divided by x, but if I multiply both sides by x to get y equals 2x, guess what? That right there, ladies and gentlemen, is linear. So I want you to pause now and answer 12 through 16 on your own. Okay, I'm going to go through this rather fast, so I'm hoping you did it. This is linear. This is linear. I can get them into y equals. This is also linear because really this says y equals 1/3 x. Remember we talked about that. This one is nonlinear. X has an exponent of 3. And 16, ladies and gentlemen, is actually linear. If I cross multiply, I'd have 5y equals 2x. And then I divide by 5, and I'd get y equals 2/5 x. Okay? 17 and 18 we will do together in class, so hold off on those. Our last way to determine is to make sure that the variables increase or decrease at the same rate. Meaning, as I move along that line, the slope is the same. In order for it to be linear, the slope must be the same anywhere on that line. Okay, so it's super important that we understand this and are able to spot it. Okay, because if not, then you won't be able to determine. So if I take a look here, as I move down, okay, from 1 to 4, that increases by 3. 4 to 7 increases by 3. 7 to 10 increases by 3. This is 1, 1, and 1. But what we must realize is, right along here, the slope between these 2 points, it's the change in y over change in x. And for this one, it was 3/1. Okay, so far so good. For this one, it was 3/1. And then for these last two, it's also 3/1, meaning it is in fact a linear function because as I move down, it stays constant. Okay, so let's go look over here. As I move down, this is +3, +5, +7. Now that's going up by 2 each time, so this could work out because if I come over here, okay, so from here to here, that slope is 3/2. That's completely simplified. When I move from here to here, though, I went up. This should actually be a 1, not a 3. Okay, so what happens here is my slope from here to here is 5. Let's actually erase this for a minute. It's actually 5/1. So right away, if you look here and you look here, those are not the same. If you want to test it and go from here to here, and you'd have 7/3, still not the same. So that's why this function here is nonlinear. So let's go look at our first example, and I will do the first one with you. Okay. From 5 to 9, I went up 4. 9 to 13, I went up 4. 13 to 17, I went up 4. 3 to 2, I went down 1. 2 to 1, I went down 1. And I went down 1. Now, if you look at your slope would be the change in y over the change in x. Okay, so it's super important that you see this. These are all your x terms right here. Okay, and then these are all your y terms right here. So since from one change to the next change, it's the same, this is linear. Okay, I want you to try the next 3 on your own. And I'm going to be checking. I want to see Is it linear or nonlinear? If it is linear, I want the constant rate of change. After that, take a break. This might seem like a lot, but it's really not. It's studying and understanding what we're looking for.